Hi, and welcome to this presentation on AiiDA 1.0, a scalable simulation platform to manage high-throughput, high-performance simulations with automated provenance tracking. This video was recorded for the Material Science track of the SciPy 2020 virtual conference. My name is Simon Adorf, and I'm going to be the presenter for this talk together with my colleague Sebastian Huber. Before we talk about AiiDA, I want to briefly introduce the problem space that we are tackling here. We are addressing challenges that we face within the realm of high-throughput and high-performance computational science, specifically those related to data management and workflow automation, with special intention to preserving data provenance and ensuring reproducibility. So what are these challenges? One is robust workflow automation. We need to have a way to define complex workflows that can deal with error states and that can be executed in a fully automated fashion on both local and remote resources. Another one is efficient data management. We want to have the option to store data that is supposed to be indexed and queried for in databases and large binary data in file repositories, using schemas that are efficient but can also adapt over the lifetime of our project. Typically, the amount and the kind of data we want and need to store changes quite dramatically between different computational studies, and sometimes even over the course of a single study. Our data management approach must therefore be flexible enough to accommodate those changes. Any data we store must also be discoverable, meaning it is not sufficient to just store everything, but we also need to be able to make sense of it later and find data we are looking for. Concretely, we want to track the full provenance of all of our data such that we can always retrace the exact steps taken that led to a particular piece of data, including the final results. All of these challenges will be significantly more difficult to address as we approach exascale. So what exactly do we mean by data provenance in this context? Data provenance in the context of AiiDA is referring to the record of how a piece of data was obtained, specifically which data transformations, such as calculations, were performed to produce it. So for example, the calculation on the right takes two input data objects and produces two distinct data outputs. The provenance of those data outputs is therefore the knowledge that they are the result of performing this specific calculation on those particular inputs. To retain data provenance, we therefore must accurately track what calculations were performed on what inputs. And further, to increase the chances that said calculation is reproducible, we also must track the computational environment. That includes, for example, the versions of all involved programs. A real workflow almost always consists of more than one calculation. Outputs of one calculation constitute the inputs of another calculation, with many different steps and sometimes complicated control flow. By representing these calculations and inputs and outputs as nodes within a graph, you obtain a so-called provenance graph in which you can retrace all steps taken to obtain a specific data object. Now, if a workflow consists of only a few steps and we execute it only a couple of times, then we can actually manually track all of these steps, for example, by keeping a comprehensive log. However, this very quickly becomes infeasible for more complex workflows. This graph represents a workflow of a molecular dynamics study. You can immediately see that creating such a graph without some automated infrastructure already starts to be challenging. However, this graph only represents the general workflow for a single material. The actual study involves hundreds of thousands of DFT calculations. This is a visualization of a provenance graph of a different high-throughput study. It is immediately apparent that creating such a graph without some automated infrastructure, or even after the fact, would be completely impossible. AiiDA is such an infrastructure. AiiDA provides all components needed to implement workflows that are reproducible and that retain the full provenance of all data objects that are consumed or produced by these workflows. We sometimes also think of it as an operating system for computational science. It is designed to support researchers who are conducting high-throughput and high-performance studies. AiiDA is implemented in Python, and parts of its API are exposed in Python, meaning it can be integrated with other Python libraries and workflows. However, AiiDA is primarily designed to integrate and execute external programs that are doing the heavy lifting and are implemented in languages that are closer to the metal, such as C or Fortran. The software is open source, so you can download it for free or use it for free and modify it if you like. We maintain all source code related to AiiDA on GitHub, and everyone is very welcome to contribute to its development. Last year, we released version 1.0 that came with a bunch of performance improvements with respect to how many concurrent computations AiiDA can manage and how quickly we can search the database to retrieve results. So let's have a brief look under the hood of AiiDA 1.0. AiiDA is a Python package that you can install on your laptop or workstation. It utilizes a lot of other libraries, including NumPy, Django, Paramiko, in combination with services such as PostgreSQL, to name just a few. With version 1.0, in particular the engine responsible for the execution of workflows and communicating with scheduler systems, is now much more scalable by distributing the load over independent daemon workers that are demonized by the Circus library. Communication with and between the daemon workers is enabled by the RabbitMQ message broker. This move from a polling to an event-based design makes the system significantly more responsive. The AiiDA storage system consists of a file system native file repository combined with a database backend with the choice of either using Django or SQL Alchemy for the object relational mapping. There are multiple ways for a user to interact with AiiDA, including the Python API, a command line tool called Verdi, and a RESTful API. Now, AiiDA is certainly not the only workflow platform for computational science, and today there are many other great frameworks out there that have similar goals. Obviously, I can't name them all, but we think it would be informative to compare AiiDA and its design choices to some of the other popular frameworks. AiiDA runs on your computer and communicates with remote computational resources directly via SSH. This allows you to easily switch between different computational resources you have access to, but can also make it a bit more difficult when that remote access via SSH is restricted. AiiDA ships with a flexible plugin system based on Python entry points that allows you to add support for your own simulation codes, data types, schedulers, etc. completely independently without ever having to change the AiiDA core codebase. AiiDA allows you to define workflows that decide during runtime which paths to take, for example, rerunning a job with different parameters if the original one failed, or performing a different set of calculations for different classes of input data. AiiDA has a strong focus on recording data provenance, including ways to do sophisticated queries on the resulting provenance graphs, and we found using PostgreSQL to be the most performant database for our use case. These choices come with their different pros and cons, and in the end, it really depends on your use case what tool works best for you. Okay, so now I think it's time to get our feet wet and see how AiiDA actually works in practice.
We will start with a really trivial example, the multiplication of two numbers. And I'm going to execute this demonstration within a Jupyter notebook, but I could use any other Python shell just as well. Let's assume that we have a number x equals 3 and a number y equals 4, and we want to multiply them just like this, m equals x times y. And then when we inspect m, we see that is an integer with the value 12, not surprisingly. The number 12 is the result of this particular multiplication, but we actually lost all information about how we obtained m if we really only had that particular piece of data. Was it a result of an integer multiplication? Or maybe an addition? And then even if we knew it was a multiplication, we still don't know what the inputs were. Was it 3 times 4, or 2 times 6, or 1 times 12? So how could AiiDA help us to retain provenance in this trivial example? First, we will define a function to perform this particular operation. So we have a multiply function, which returns x times y. And then we will declare this function to be a calc function by applying the calc function decorator. The specifics of what that means aren't important for this example. The only thing we need to know is that by applying this decorator, we instruct AiiDA to keep track of both the inputs and outputs of this particular function. Then we need to tell AiiDA about our inputs. That means we need to declare them to be part of the provenance graph by explicitly assigning them to a known type using the ORM. In this case, int. So we have x equals 3 and y equals 4, just like before. And we will then execute the multiplication. And when we inspect m, we see that it is of type int with value 12, and it has been assigned a ID, which means it is stored in the database and has automatically been made part of the provenance graph. The Verdi command line tool has some neat commands to automatically visualize those graphs. We see that a PDF was created, so let's open that. The graph tells us that this integer value 12 was the result of a multiply calculation with inputs 3 and 4. Obviously, this example is somewhat contrived and admittedly trivial, but I hope I was able to demonstrate how AiiDA can help us in automatically tracking the provenance of data. Sebastian will now show us a slightly more realistic example that involves a workflow with multiple steps and the integration of external programs. But all the basic principles will be exactly the same.
Thanks, Simon. In this demonstration, we will show a real-world use case of AiiDA in the field of material science, where we will compute the total energy of a silicon crystal structure. We will be using the Verdi shell, which is an interactive Python shell that ships with AiiDA. First, we import the crystal structure as a CIF file using the database importer plugin for the crystallography open database. We can load the importer class using the factory and the plugin entry point. Next, we use the importer to query for the ID of the structure that we want to compute the energy for. In this case, I already know exactly what the ID is of the silicon structure. The importer will automatically store the source metadata in order to maintain full data provenance. The next step is to clean the imported CIF file and parse the crystal structure from it. For this purpose, we will use a workflow from the AiiDA CodTools plugin package. Just like the database importer, this workflow is a plugin and can be imported with the corresponding factory and entry point, which is in this case codtools.cifclean. Let's have a look at its specification to see what inputs it requires. We can define the inputs as a dictionary whose structure matches that of the workflow specification. Now we can launch the workflow by using the run method of the engine module. We can see the reports from the work chain as it is running the various cleaning and parsing steps, which are also stored in the database as part of the provenance. Now it's all done. Let's have a look at the results and visualize the parse structure. Finally, to compute the structure's total energy, we will use a workflow from the AiiDA Quantum Espresso plugin package that uses the Quantum Espresso DFT software distribution. As we can see, it defines many inputs. Instead of providing those as a single dict as we did before, we will now instead use a builder, which is a utility that offers tab completion to automatically discover all the inputs. To launch the workflow, we simply run the builder. In this example, we are running this calculation on my local host, but just by changing the code, AiiDA can just as easily run this over SSH on a remote machine, with automated and built-in support for job schedulers such as Slurm, Torque, and PBS. Once the job is done, the results will be automatically retrieved and parsed. For this workflow, the total energy is stored in the output parameters dictionary node. And there we have it, the total energy. With a single command, we can now generate a graph of the entire provenance of this computed result. The entire history, all the way to the original CIF file that was imported from the external database, has been automatically saved by AiiDA, making our final result completely reproducible. And with this, I would like to end this demonstration.
Thank you very much, Sebastian. Before we finish, I would like to provide some brief background information on the development history of the project. Starting from ideas from earlier prototypes developed at Bosch RTC in the US and EPFL in Switzerland, we jointly designed and wrote AiiDA from scratch from late 2012 with the first open source release in 2014. The code was continuously improved until about 2016, at which point it became clear that a major redesign was needed, which converged in the release of version 1.0 in late 2019. Throughout its development, AiiDA has been used for production in scientific projects, and while the code has gone through API-breaking changes for version 1.0, we have ensured that datasets created with older versions of AiiDA can still be imported, queried, and operated on. Since preserving data provenance and reproducibility are at the core of AiiDA's goals, we have invested significant time and effort into writing and testing data and schema migrations, and you can expect us to continue to do so going forward. AiiDA has been designed from the start to be modular, such that it is easy to contribute domain-specific plugins not only for material sciences, but for any domain that can benefit from this infrastructure. We maintain a public registry of plugins that as of this moment has 50 entries, which means that many codes typically used in the computational material science community are directly supported. Some of these plugins are developed and maintained by the AiiDA team, but many others are directly contributed by the wider community, both in Europe and elsewhere. And while most of these are currently focused on the material science community, we hope that we will be able to expand towards other domains going forward. We do an annual survey of AiiDA-powered research projects on the AiiDA mailing list to learn how AiiDA is used and where to direct efforts for future developments. This year, people submitted 69 research projects at various stages of completion, using a wide range of plugins and from 11 different countries. You can find a list of scientific papers using AiiDA on aida.net/science. Over the last years, we've seen a steady growth of the AiiDA community, which we try to support by hosting regular workshops and tutorials. In fact, we are hosting one tutorial at a time of this SciPy conference. These tutorials and workshops are targeted at users of all levels, from newbies to experts, and are also an excellent opportunity to learn about community needs and pain points. We have lively mailing lists for both developers and users. We are happy that AiiDA is now a non-focus affiliated project as of earlier this year, which among other things gives us the opportunity to participate in the ongoing Google Summer of Code. And when you have performed your calculations using AiiDA and are ready to publish your paper, you can upload your AiiDA database to a material science repository to make it fully reproducible. This can be any institutional or domain-specific repository of your choice, including the Materials Cloud, which is a platform that allows you and your collaborators to directly explore the provenance graph of any uploaded AiiDA database. The platform is not limited to AiiDA data, but AiiDA is to the Materials Cloud like Git is to GitHub. The former is the tool that each individual researcher uses to produce and curate their data, while the latter allows them to share their workflows and data with the world. We think that both components, the tool and the platform, are essential for reproducibility and data fairness. So where are we heading in terms of development? There are a number of feature developments we would like to accomplish, such as the native support for containerized calculations, replacing the current file repository backend to get better performance and storage efficiency, enabling bulk operations on nodes within the provenance graph, and a lot of other exciting things which you can find on our public roadmap if you're interested. There are also some broader efforts that are not directly related to the core code base, such as the developing standards for common workflows within the domain of material science, but also expanding beyond our home domain and reaching more users and other fields. In conclusion, AiiDA is a platform for computational science that helps you keep track of data provenance of your calculations and to share your results in a reproducible way. With the major performance improvements with version 1.0 last year, AiiDA now supports workloads with tens of thousands of concurrent processes. None of this would be possible without the large number of AiiDA developers, whose names are listed here, led by Giovanni Pizzi and Nicola Mazzari. We are lucky to have long-term structural funding for this effort. Marvel is a Swiss National Center of Competence started in 2014 and potentially running until 2026, which includes resources dedicated specifically to developing an open science platform. We are also supported by the Max European Center of Excellence for Materials Design at the exascale, with a focus on providing the tools enabling the convergence of high-performance computing, high-throughput computing, and high-performance data analytics. Additional funding and support is provided by the European H2020 Marketplace and Intersect projects, PAC, the EPFL Open Science Fund, TRACE, ERC, Swiss universities, and the European projects EMMC and NFFA.